A scientist is testing models for the growth and decay of colonies of bacteria. For a particular colony which is growing, the model is P equals A e to the T over 8, where P is the number of bacteria after a time T minutes and A is a constant. This growing colony consists initially of 500 bacteria. Calculate the number of bacteria according to the model after 1 hour. Give your answer to the nearest thousand. For a second colony, which is decaying, the model is Q equals this, where Q is the number of bacteria after T minutes. Initially, the growing colony has 500 bacteria, and at the same time, the decaying colony has 500,000 bacteria. Find the time at which the populations of the two colonies will be equal, giving your answer to the nearest 0.1 of a minute. The population of the growing colony will exceed that of the decaying colony by 45,000 bacteria at time T minutes. Show that this equation holds, and hence find the value of capital T, giving your answer to 1 decimal place. So it's a long question, isn't it? And I've broken it up into step-by-step stages. Hopefully these stages will be fairly straightforward for the most part. So let's have a little look at it then. Hopefully it takes longer to read than it does to do it. Initially, calculate the number of bacteria after 1 hour. So T equals 0. P is equal to A. Put T as 0 in here, and we get e to the 0. E to 0 is 1, so that's just A, and initially it's 500, isn't it? So A equals 500. So that's what we've got there. So at T equals, now T is measured in minutes, so after 1 hour that's 60. P is equal to A, which is 500, E to the 60 over 8, isn't it? Which equals 500, E, 50 over 4, 25 over 2, 12.5. No, sorry, 30 over 4, 15 over 2, 7.5. That's what it is, 7.5. We can tap it in the calculator if we need to. Now we need to work this out to the nearest 1,000, don't we? So 500 times E to the power 7.5, or 60 over 8, wasn't it? Equals, so 904,000 is the nearest thousand, isn't it? 904,000. To nearest thousand. Okay, there we go. And that's part A then, we've done that there. Now move on to part B. For a second colony which is decaying, the model is this. Initially the growing colony is 500 and the decaying colony is 500,000. Find when the populations are equal. Okay. So I'm going to move this second part out of the way just for a moment. We'll come to that in due course. Let's just get some room here. Okay, so we're told for part B then. Initially, the decaying colony is 500,000. So T equals 0. Q, the population of the decaying colony, is equal to 500,000 times e to the T is 0, so e to the minus 0 is e to the 0, which is 1. 500. Yeah, that's fine. Which is fine, that's fine. No further information is there. Find the population, find when the populations are equal to the nearest minute. So here, when does this 500,000 then? E to the minus T over 8 equal, let's have a look what we've got. A is 500, e to the T over 8, so it's 500, e to the t over 8. Okay, well we cancel by 500 both sides. There's a 1000 there. And then we can multiply through by e to the t over 8. So 1 is equal to 1000. See, and then bring that down, and in a sense you're timesing both sides by e to the t over 8. So it'll be e to the 2t over 8. So when you times this by e to the t over 8, times you add, and that will become e to the 0, which is 1, which is fine. And here, times this by e to the t over 8. This times itself, or you add the powers, you get 2t over 8. So that tells us then, that's t over 4. The 2t over 8, which is t over 4 as we said, is equal to, now move the e down, it's log e. To do the log, you swing this down as the base number, this drops down to ground level, and it's log e of 1000. Log e of 1000. So t is equal to then, move the 4 from divide to times, ln 1000. Okay, 4 log 1000. So let's tap that out. 4 times ln of 1000 equals 27.63 to the nearest 0.1 minute. This is in minutes, so it's 27.6. To nearest 0.1 minutes. Okay, so that's what we've got there. So that's part 1 then. Now part 2, which we'll move back up now to give us as much room as possible. Here. Right, the population of the growing colony will exceed the decaying one by 45,000 at time t. So the growing colony is 500 e to the t over 8 at time t. Take away the decaying colony, e to the minus t over 8, and that equals 45,000. Okay, good. So let's just divide by 100 all the way through. Divide by 100. Divide by 5 all the way through as well. That's a 1 now. That's a 1000, isn't it? And divide this by 5, we get 90. And then multiply by e to the t over 8 now. So here we get e to the t over 8 squared minus 9 t, 9t, 90, over here is minus 90, and we're multiplying by e to the t over 8, aren't we? Minus, when we multiply e to the t over 8, this will be e to the 0 then when you add the powers, so it's just minus 1000. And that will equal 0, which is what we wanted to show. Okay, we've done that then. Show that, and hence find t to 1 dp. So, what have we got? 10 hundredths? I reckon it's 10 hundredths with a difference of 90. It's a quadratic. So, here's our quadratic term, so to speak, t over 8. And we said 10 hundredths because that looks promising. This is minus, so put a minus and a plus. Let's see if we've guessed correctly. This would be squared when we expand it. Minus 100 plus 10 is minus 90, lots of these things. And then plus times minus is a minus 10, 100s are 1000. So that tells us then, e to the t over 8 is always positive, so this can't have any solution. And e to the t over 8 then is equal to 100 is the other solution. So that tells us that t over 8. So swing this down to be the log, ln 100. So t is equal to then, Move the A tab, 8 log 100. That looks fine. So we need this to 1 dp, don't we? So let's just get the calculator. 8 times natural logarithm of 100. 36.8. And that's minutes. And that was to nearest 0.1. Okay.